92 inches cube. Okay, this is Q. So if you were to ask if I'm going to write this properly, this is the first moment of area, Q, about the z-axis. Okay, that is our QZ. Right. So now once we have this, right, we will know that V over I, so the shear stress is equal to V over I at point, sorry, V over I at point A. Let me, shear stress at point B, sorry, is equal to Vy over Izz, right, Qz divided by T, right? So I don't know what is Vy. I did not calculate Izz. We know Qz is equal to 0.392. And then the thickness, right? The thickness is, you have to consider what? You have to consider 2, okay? You have to consider 2 multiplied by what? 0.2. Why 2 over here? Because of the 2Q, right? We wrote 2Q down here, the 2Q. So you have the left and the right. So this is equal to 0.392 divided by 2 divided by 0.2 is equal to 0.98, right? Vy over Izz. Now the question comes to this. Why, right? I just put it as a variable. Can someone tell me, okay, can someone tell me why did I leave Vy over Izz as a variable? Anyone? Can anyone tell me why?
Because they're constant, so you can cancel them out later on.
Yeah. Okay, they are constant. Well done. Okay, we can cancel them later on. Okay, we can cancel them later on. Now let me, who answered that? Where are you?
It was me.
The Ranger, you're right. If we were to look at, if we were to, come on, you are not allowing me to zoom in, zoom out. Today I'm not having much luck with Microsoft. You know, usually I'm very good at it. Today I'm just not very good at it. So what do I, what does Rajinder mean by that? Okay. So later on, when we find the shear stress, right, at point A, so this will be equal to Vy over Izz, right? And then we are going to have a constant. And this constant over here will be equal to what? Will be equal to Qz over T, right? That is why we are, and then, you know what is the interesting part, right? This question, let me go to this one. This question specify that the maximum shearing stress is 10 ksi, okay? And find the stresses at point A and point B. At this stage, right? If I review you the full diagram, where is the location of the maximum shearing stress? Anyone? Can anyone tell me? So we don't know. That's where we talk about the marking of the quiz earlier, right? We don't know. So we have to check. Right now, I'm telling you now, I'm not a clue where it is. Okay. So there's another point that we have to check. Another point that we have checked is to check at point C. I'm going to call this point C. Because point C is at the centroid, and in terms of shearing stress, right? You know this. In terms of shearing stress, the centroid will have the highest shearing stress. Okay, but what is the controversy is this: the thickness at the centroid is the highest. Can you see that? The thickness is higher. So if the thickness is higher, the ratio will change by how much we don't know. Okay, we are engineers. We have to quantify them. Okay, so for this course, I know there is no set procedure. Okay, but I want you to have the habit of checking. Okay, is this the location of the maximum stress? Okay, right. So now we found out at point A, right? We found out the stresses at point B. The ratio is, we found the ratio to be equal to what? We found the ratio to be equal to 0.98 Vy over Izz. Okay. Now next, we want to look at point A. Okay, we are going to look at point A. So I'm going to, hopefully I can copy this diagram. Okay. And I'm going to paste. Okay. And then I'm going to sketch our centroid. You sketch our centroid. Okay, so this is our centroid, right? So this will be our centroid. And then next we are going to look at, I'm going to cover it. Okay, just not cover. Now I'm going to do this. Okay, and I'm going to cover the top. Then I'm going to construct the shear flow. Okay, we're going to construct the shear flow. The top is easy to look. Now is point A. Okay, so we want to find, right? We want to find the shear stress at point A now, right? So you look at this, right? What sort of analysis is this, right? What sort of it? So if you look at the, if this side is called our left and the other side is called our right, right? Question for all of you, right? You can see that now, right? Question for all of you now. Is the left shear flow and the right shear flow link after the centroid? Anyone? Is the left central is the left web or the left section and the right section link after the centroid, the shear flow? Anyone? Is it linked? The answer is no, right? It's only linked when it is the what? When it is, if I cover here, right? If we look at the top, it's only linked at the top, right? Because the top is box beam, right? At the bottom, right? At the bottom, right? It is not linked, is it? The left Q, so this I call it the Q left, and the Q right, they are not linked at all. Yes or no? They when I say they are not linked, right? If you look at the bottom part, they are not starting from the same terminal. In fact, they end in separate terminal. These are all our terminals. So for the fact that this is the case, is it a box beam or a wide flange? Okay, so now coming back to here, right? Coming back to the theory. Now it's more like a what? It's more like a what? It's more like a wide flange because you have two what? Two separate terminal. Yes or no? Okay, so now Okay, now the analysis is white flange, right? And now it's no more 2Q. Because at point A, it's only Q on the right-hand side, yes or no? Right? There's only one Q, right? Before that, you have Q going towards the left, towards the right. Well, at point A, you only have one Q value. Now, some of you might say, Eugene, this why can someone explain to me? Okay, let me ask you the question. Can someone explain to me why, right? Why we only look at A and the area to consider? I'll give you guys. I'll write this out. The area to consider is where I'm shading blue now. Can you all see the blue? Yeah. No, that is not. This is the area that we're going to consider. Can someone tell me why? Anyone? Why that is the area to consider?
Because it has a smaller thickness?
No, that's not the reason. Because of rule number what? Rule number 3. The analysis starts from where? Starts from Y max. So at the bottom, right? This is your what? Right? So the analysis direction is going back this way. Okay. So let me amplify that A area, right? So A is exactly over here, right? The analysis direction is going back towards the what? Right? The analysis, this is our analysis direction. Right? So if this is our variable y, right? This is our y variable. So the y variable will shift, right? Will move with time, right? So when it moves to this distance over here, y, right? This is the only area of concern. We are not interested in what's going on in this area, in this region. Does that make sense now? Yes or no? Okay. Right? Because the analysis direction starts from what? Y max. Yes or no? Okay. That's why those 4 rules or the 5 rules now are so important. Okay. So in this context now, we know, right, how to find our Q. Okay. So again, now don't worry if this is the first time you're seeing this. Don't worry if you're not getting it yet. I'm going to do more examples. And when I do more examples, you are able to look at the trend. Okay, I'm going to go slow on this. Okay, so the shear stress at point A is equal to Vy over Izz, right? And then it's Qz divided by T. Okay, right? And we know T is equal to 0.2 inches. T is not 0.7, yeah? Because the thickness is perpendicular to the shear flow. I repeat again, the thickness is perpendicular to the shear flow. Okay. So with this in mind, right? So now we no need to find Vy, as we need to find Qz. Okay. So now Qz, again, we'll use width multiplied by depth multiplied by y bar. So the width is equal to 0.7. The depth is equal to 0.2. The y bar is 1.5 minus 0.2 divided by 2. Okay. So 1.5 minus by 0.1 times 0.7 times 0.2 is equal to 0.196. inches cube. Okay, so the shear stress at point A is equal to Vy